Okay, class, welcome to lecture 22. So today we're talking about hypothesis testing for means, which is slightly different than last time, but it's very similar. And in fact, we are going to start off by doing one more example of hypothesis testing for proportions before we do means. So that's what we're going to do first. There's one last type of example we didn't get to. Okay, so here is the example. A 2009 study found that 34% of teens text while driving. There's a more recent study which found 353 out of 1,200 randomly selected teens text while driving. Suggests the proportion has changed. Use alpha equals 0.05 for the significance level. Okay, so the idea is, how is this different than the previous ones? The main difference is that the alternative hypothesis is not a less than and it's not a greater than like it was last time. It's going to be something else. So the null hypothesis, though, is still going to be that a proportion equals something. So the idea here is that a different study, this one, is suggesting that the true proportion of teens that text while driving is 34%. So our null hypothesis is that that is correct, that that's the true proportion. And we want to see if our sample suggests that actually that's wrong. But in this example, we're not saying how it's wrong. We're not saying if we think it's actually more than 34% or less than 34%. We're not saying either of those. We're saying we just want to know if it has changed at all. So here we're not specifying more or less. And so that's going to tell us that our alternative hypothesis is that the proportion is just not equal to, which we write like that, 0.34. We're not seeing if it's more or less. We don't know. We're just saying it's not 0.34. We think 0.34 is wrong. That's the alternative hypothesis. Okay, so that's the main difference on this type of problem. And when it is like this, we can do the problem using confidence intervals. And it's a little bit easier than what we did last time. So that's why it's nice to do it this way. So to actually run the hypothesis test, we can create a 95% confidence interval, which we know how to do from a long time ago. So why 95%? Well, that's because alpha is 0.05. So if alpha was 0.01, you would do a 99%. Or if it was 0.10, you would do a 90%. So that's just going to depend on alpha. Okay, so remember how we do that. I need a sample proportion, which I have. It's 353 out of 1,200 because this is my new sample that I am checking if it's so crazy that it makes me question the original proportion being true. That's the idea. So this is going to be about 0.294. And then you need a critical value to make a confidence interval. And because it's a 95% confidence interval, I can go look up in a table that the critical value for that confidence level is 1.96. So that's not any work to do because I'll just give that to you like on a quiz. So that's good. And then I need a standard deviation. Of the sampling distribution. It's a little bit different than before. So when I made confidence intervals before, I keep going back and forth on this. So I used this to do the confidence interval. So I used this sample proportion. But remember that I was doing that because in those problems, we didn't know the true proportion. So this was just our best guess for the standard deviation by using our sample proportion instead of the true proportion because we didn't know it, because the whole point of those problems was create a confidence interval to estimate where the true proportion is without actually knowing where it is. But now in this problem, we do know the true proportion, or at least we are assuming a true proportion. It's this, 0.34. So we're not going to use that. We're going to use the actual formula for standard deviation of the sampling distribution, which is p times 1 minus p over n instead of p hat, and then I'll square root of all that. So because p is 0.34, that's what I'll use. So 1200 is the sample size, and square root that whole thing. Okay, so that's going to be the standard deviation that I'm going to use for this confidence interval. So a little bit different than when you make a confidence interval. Different type of problem, slightly different standard deviation. Okay, so just keep that in mind. Very big warning there. So then what do we do next once we have our standard deviation? We got to get the margin of error. So that's just going to be your critical value times your standard deviation. That's the same as before, using this formula for standard deviation. Okay, so you'll get that. So then what's the confidence interval? Well, now it's just our sample proportion. So this is p hat plus the margin of error. Oops, 0.27. And I also do p hat minus the margin of error. 0.27. So that'll give me the confidence interval. So this is 0.321 and 0.267. Okay, so now how do I use this? So I'm not actually making a confidence interval in for the same purpose as when I make confidence intervals in those other problems. Now what I'm looking at is whether or not the true proportion is in this interval. So is it from 0.267 to 0.321? No, it's bigger. It's 0.34. And what this means, the way we're thinking about this, is that our sample proportion is too far away from the assumed true proportion. So this is just another way to find if our sample is too weird so that we can reject that this is the true proportion. That's the idea. So reject H naught. If it was in there, we would not reject H naught. Okay, so let me write out a little bit of explanation. So this is because, so why is this working? This is because it has to do with how confidence intervals work. We can be 95% confident that our interval that we just created contains the true proportion. And so ours doesn't contain this assumed true proportion that means something weird is happening. So since ours does not contain the assumed p equals 0.34, this is evidence that that proportion might not be the correct proportion. And that's why we reject. When this happens, that's why we reject. Of course, you don't have to explain it every time you do it. You just reject it. But that's why you're rejecting it. Okay, so then what's the conclusion? Just like before, still got to have a conclusion. There is sufficient evidence at the alpha equals 0.05 level to suggest that, now the context comes back, but really what this means is we're accepting H1 instead, that P is not 0.34, and now I'm just rewriting what that actually means in context of the problem. So in context of the problem, we're saying that the proportion of teens that text and drive has changed. That's really what this is saying. From math to words. Okay, so in all the examples we've done so far, I keep making it so that there is enough evidence to suggest that blah de blah happens. So just so you're aware, so let's just pretend for a second that if P was like 0.3, because then it would be in there, we would not, oh, I accidentally used that marker. We would not reject. Remember, you don't accept the null hypothesis. You just don't reject it. Instead, and how would that change your answers here? You would just say there is not sufficient evidence to do this. And that's it. Okay. All right, so just one last thing. I didn't do the checks, but they are actually necessary still. Remember those checks I did last time? You do have to do them. I was just doing the math only. Okay. All right, so now we can do means. Hypothesis testing for means. So that was all for proportions. It's all the same idea, but different math. But that is, you're going to assume the null hypothesis is true. You're going to get a sample, but instead of a sample proportion, it's going to be a sample mean, and see if it's too strange, which will be where the math is different this time. But you're seeing if it's too strange. If it is, then you get to reject that H naught was true. Okay, so let me pop in an example. So this time I'm not going to do all the theory because the theory is the same, just a little bit different math. I'm just going to jump right into examples. So let me pop it in here. Okay, so here's the problem. The mean height, so now we're talking about means, of American males is 69.5 inches. Heights of the first 43 presidents have a mean of 70.78 inches with standard deviation 2.77 inches. We're just going to pretend that this is like some random sample. And then we're going to determine if there is evidence to suggest that US presidents are taller than average using this significance level. So we're really running a hypothesis test. here where we are assuming that the standard, the average height is 69.5, and we have this sample mean, which is bigger, and we're going to see if it's so far away, if it's so weird, so much bigger than average, that we can claim that 69.5 is not the actual mean, and in fact it's bigger for presidents. That's the idea. Okay, so writing this more mathily, what I just said, what we're doing is we're assuming that the mean, which, because it's the mean, not a sample mean, I use mu. We're assuming that this mean is also true for US presidents. And then we're seeing if our sample mean, so we didn't have to calculate the sample mean, which would take forever. We're just given it immediately, 70.68. We're seeing if our sample mean, which also comes with a sample standard deviation, which again, we're not calculating ahead of time, or we're not calculating now, they're giving it to us ahead of time, thankfully. We're seeing if this is so strange, meaning something mathy, which comes in later, that that we question whether the 69.5 could possibly be the mean for presidents. So we're questioning whether it could possibly be the mean for presidents, but also specifically that it's going to instead be bigger. So the reason we're thinking it could be bigger is because the problem is asking us to think about if the evidence suggests that US presidents are taller than that average. If it said shorter, then we would be doing a less than problem. If it said different, then it would be a not equals problem. That's what we're going to always see when we write down the null and alternative hypothesis. Okay, so these steps are going to be applicable to other examples too, and they're very similar to the steps for proportions. So we're first going to write down our null hypothesis. So now our null hypothesis is about means. So our null hypothesis is that the mean height of US presidents, that's what this mu is standing for, is 69.5, versus our alternative is that no, actually it's bigger, that it's taller. It's bigger because they're taller on average. And we're seeing if our sample is enough evidence to suggest that. So now we need to get a sample mean to do the math, and that's just given to us, luckily, so we don't have to actually calculate it. 70.78. We also need a sample standard deviation. Again, that's just given to us, luckily. Otherwise, you would have to calculate it from a bunch of data. And then you need a significance level. So very similar to the proportion problems, you're sort of just compiling a bunch of information at first, and then you're going to just put it all together to do the problem. Next, we're going to get a test statistic. That's just like last time too, but now our test statistic is, instead of a z-score, it's going to be a t-score, because if you remember when we did confidence intervals, they were all, for means, they were always on the t-score distribution instead of the the normal distribution. So we had to use t values and t-scores over there. Same reason over here. So now we're going to find the t-score instead of the z-score like we would in the other types of problem, the proportion problems, of our sample using a formula. It's going to just be a sort of magic formula. Well, it's not that magic. It looks very much like the z-score formula. So instead of calling it z0 like we did for proportions, we're calling this t0. And it's going to be, well, it's our thing, how far away it is from the actual thing. Same idea as z-scores. So our sample was this x bar, and the actual mean is mu. So we're going to see how far away it is from the actual mean. Then we're going to divide by the standard deviation, but the standard deviation of the t distribution, not just the standard deviation s. So it's s over square root of n. That was what we saw a long time ago. That's the standard deviation, not just s. Okay, so you got to take into account the sample size. So it's very much like a z-score. This is how far, instead of in terms of standard deviations on a normal distribution, it's how many standard deviations you are away on a t distribution. So this is how far our sample is from the mean, or the assumed true mean. So remember, we're really just seeing if our sample is so far away that it's too strange, and it makes us question the original mean. So this is exactly saying how far away it is, but on the t distribution, which we really didn't study very much, but we are going to have to use it. That's okay. Okay, so we don't really have to know much about it to use it, because we just need this little formula. So let's calculate some stuff. So first of all, what is s over square root of n in this problem? That is going to be 2.77, my sample standard deviation, and the sample size, there was 43 presidents. So that's where that is coming from. Okay, so that's going to go under there. So then my T0, my test statistic, if you want to use the fancy language, is 70.78. That was my sample mean. Now I'm seeing how far away it is by subtracting it from the supposed true mean. And then I want to see how many standard deviations away it is on the t distribution. So I divide by the standard deviation of the t distribution. Okay, so this will be 3.03. So 3 standard deviations is probably going to be very far away, and it's going to tell us it's too far away. Okay, but now we got to say that in the right way. So that's the next step. So we don't have a threshold yet. That's where the significance level will come in. So next we need threshold. So that was our critical values last time. I think that's what I named it, but it was just a z-score corresponding to the alpha. But now we need a t-score. So we need a threshold to see if our t-score is too strange. So all we got to do is use a t-score calculator. And then in that t-score calculator I gave online on Moodle, I can plug in this significance level, which was 0.05, and the degrees of freedom, which is always 1 less than the sample size, so 42. And it'll tell us something. So I'll just write what it'll look like. It'll look like something like this. Two-tail. It'll say two-tail, t equals, and then it'll have a plus or minus 2.018. And it'll also have a one-tail. 1.682. So it's going to give you two answers, basically. Which one do we want for our problem? We use this one. And it's because we are checking, an alternative hypothesis where we have a greater than symbol. So we're checking, really, what this is really saying is we're checking if our t-score is too far to the right. Meaning we're just checking if it's too far on one side. That's the key word, one side, one tail. And specifically which side, the right side. And that's because of this. So in pictures, what's going on here is we have a t-distribution, which looks, remember, very much like a normal distribution. It's almost indistinguishable. And this 1.682 is maybe like right there, and it signifies this much area to the right. But we don't even have to think about area in these problems, which is nice. That's what is going on. Whereas if you do two-tail, then you have to cut that area in half. So we'll do an example like that later. And so luckily we don't have to really worry about that. All we have to do is see like, okay, that's that. Our t-score is much further away. It's much further to the right. It was like 3.030 or something. So it's way past the threshold. Anything past this threshold is too far. Ours is not only past it, but way past it. And because of that, the next step is we reject the null hypothesis. And it's really because our t-score is too weird, meaning it's too far, is beyond the threshold of weirdness. I don't know how to spell weird, so I'm gonna write strange. I before E or E before I, nobody knows. Okay. And then the conclusion, of course, with context. So we always like forget the context for a long time. You got to go back and read the problem, but it goes the same way. There is sufficient evidence because we rejected. Otherwise, we would say there is not significant evidence. But in this case, there is sufficient. Sorry, I said significant. I meant sufficient. There is sufficient evidence. You have to say at what level, because it could change depending on what level you decided at the beginning. To conclude what? Well, really, we're accepting the alternative hypothesis, which is that the mean is actually bigger than 69.5. So in words, we're concluding that the US presidents are taller than average. Okay, so that's that. All right, so I'm going to do another example of a different kind. And then I will. Okay, I think I cut myself off mid-sentence, but I wanted to pop in the example. So here it is. Snickers are supposed to weigh 20.1 grams. So again, this is a mean problem because this is saying like, okay, on average, they're supposed to be this amount. Then we get a sample of 11 of them, 11 random Snickers that we pick, and we get a mean. So this is going to be a sample mean. And we get a standard deviation. So that's going to be a sample standard deviation. We want to know if this sample suggests something. In this case, does it suggest that the actual weight is different from 20.1? So the key word here is different, not more, not less, and that's going to affect our alternative hypothesis. Okay, and then we have finally a different level of significance. We usually use 0.05, but this one's a little bit different. Okay, so we're just going to follow the same steps, but now we're getting a little better at it, so we can go a bit faster. All right, the null hypothesis is that Snickers do actually weigh, on average, 20.1. So we're claiming that the mean is actually 20.1, but we want to see if instead it's different. So the keyword different is telling us that we want to check if we have evidence to suggest that it's actually not equal to that number. And we're not specifying if that we think it's more or less. Specifying. And that's why it's a not equal instead of a greater than or less than. Okay, so that's first step, slightly different. Second step, we need a sample mean. Once again, that's just given to us, so we don't have to go through that big old hassle. We need a sample standard deviation. That's going to come from what they give us as well. And I didn't write this last time, but you can also write the sample size, because we are going to use that later, and it's 11. Because I'm sampling 11 Snickers. Okay, next I write down the significance level. Really, I'm just reminding myself I don't have to write down because I can just look back and see it when I need it. And then the mathiest part of all, which is calculating this test statistic. That's going to work just the same as before. So I'm going to see how far away my sample mean is from what I'm pretending or hoping or assuming is the actual mean. And I'm seeing how far it is on the t-distribution. So I'm dividing by the standard deviation of the t-distribution, which comes from the standard deviation that you're given, divided by the square root of a sample size. Okay, if you have a fancy calculator, you can plug this all in at once, and you'll get 1.042. Or you could do it piece by piece. But you should get something around there. Maybe you round a bit different than I do. That's okay. So then I have to calculate the threshold for whether this t-score is too weird. Can't spell weird. That's close enough. I'm looking now for a threshold t-value, t-score, which tells me if this is too weird or not. So I use my degrees of freedom, which are 10, which is 10 because the sample size is 11. I put in my significance level, 0.01, into a t-score calculator. And this time we're going to use the two-tail, which is going to look something like this, plus or minus 3.169. And the reason we're using two-tail is because of our alternative hypothesis having a not equals instead of a greater than or less than sign. And again, when you're doing a not equals, what's really going on, we don't have to think about area if we don't want to on these problems, is now we're looking for this amount of area total on the right and left being 0.01, which means each side is half of 0.01. And the t-scores that give you that are these right here. That's why there's a plus or minus, because it's plus on the right and minus on the left. And then, so if you're doing a not equals, you're always looking at if it's either too far to the left or too far to the right at the same time. Okay, so in any case, ours is 1.042, so it's not very far at all, actually. And so it's not past the threshold on either side. So when you do a two-tail, you're looking to see if it's too far over here or too far over there. Either one. In this case, it's neither. So finally, we're not going to reject the null hypothesis. First time. So our T0 is neither to, let me be more specific, it's neither to the right of 3.169, nor to the left of the negative version, our threshold. So we really have two thresholds when we have a two-tailed problem like this. So because it's not too weird, we do not reject H naught. But that really doesn't change our world so much. All that happens now is that in our conclusion is we say that there is not enough evidence, sufficient evidence to suggest that the alternative hypothesis is true. So we're not accepting H1 this time. Remember, when you don't reject H0, that's all you do. You don't ever accept H0. So all we get to do is say that there's not enough evidence to suggest that the alternative is true. So now we write that back in context. There's not enough evidence to suggest that the mean weight of Snickers is different from what was claimed. So again, we're not accepting that this is true. We're never accepting that the null hypothesis is true. We're just saying that we didn't find a weird enough sample to think it's wrong. So it could be true, but we're not saying it's true. We're just saying it could be true. So that's the subtle difference of saying that we're not accepting H1. That's fine to say, but you're not supposed to say that you're accepting H0. Because if you don't get a weird sample, that doesn't mean that your claim was true. It just means you didn't get a weird sample. So you can't think it's false. But evidence supporting your assumption is not good enough because you can't ever prove something is true if you're assuming it's true. Okay, so that's sort of technical stuff to think about. But in any case, this is the end of the problem. So next time I will do another example. This video is long enough. And so that's going to be it for this. See you later.